Welcome to lecture 5 on module 1 of computer organization, in which we will be discussing about the number representation and the various processes that are involved with respect to the numbers, that is binary numbers in the computer system. The next series of lectures is on part 2 of module 1, in which we will be discussing about the machine instructions and programs. In this part, we will be introduced to the numbers, arithmetic operations and characters, IEEE standards for floating point numbers, memory locations and address, memory operations, and instructions and instruction sequencing. These are the topics that we are going to cover in the coming series of lectures. In this particular lecture, we will be discussing about the numbers in the numbers, arithmetic operations, and the characters. We will begin with the number representation. Let us consider a n-bit vector, and it is represented as b n-1 b1 b0, where bi either it will be 0 or 1 for 0 less than or equal to I less than or equal to n-1. That means let us assume n equal to 3. Now this b will be equal to b3 minus 1, that is b2, b1 and b0. These b2, b1, b0 can have the value either 0 or 1, 0 or 1, 0 or 1. For 0 less than I less than n minus 1. Here n is 3. So value of I can be 0, 1 and 2. That is, value of I can be 0, 0, 1 and 2. These vector can represent the unsigned integer values v in the range from 0 to 2n minus 1. That means in the same example, the range of numbers can be from 0 to unsigned. If it is an unsigned number, it is from 0 to 2 power n, that is 2 power 3 minus 1, that is equal to 2 to the 4, 8 minus 1, that is 0 to 7, 0 to 7. So using this particular vector, you can represent the numbers from 0 to 7 using b2, b1 and b0. So these systems can be represented. There are 3 ways to represent these numbers. However, I said that the numbers using this vector, you can represent the numbers ranging from 0 to 7. These numbers can be represented in 3 ways: sign and magnitude, 1's complement and 2's complement. So here we have 2 types of representation. Here this particular bit B0 is considered as the least significant bit, or LSB, and this is considered as MSB, that is most significant bit. So this MSB bit represents the positive. If this value is 0, that represents the number to be positive. Positive number and negative number. There are 2 types. So if the number is positive, the MSB bit is represented as 0, and if the number is negative, then it is represented by 1. However, to represent these, we have 3 ways, that is sign and magnitude, 1's complement and 2's complement. In detail, we will look one by one in the next slide. Here, in this particular example, we have taken n equal to 4. Previously I said that we have taken the example with n equal to 3. Now in this particular example we have taken n equal to 4. So the value of I ranges from B3, B2, B1 and B0. That's what is represented here. So these B2, B3, B1, B0 can have ranges from values ranging from 0, 0, 0, 0 to 1, 1, 1, 1, all the possible combinations, right? That's what represented here. It ranges from 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and so on here 1, 0, 0 to 1, 1, 1, 1. So in case of sign and magnitude, I said that we have three ways of representing a number: sign and magnitude, ones complement and twos complement. In case of sign and magnitude, we have a MSB bit, that is bit B3, that represent the sign of a number. B3 always represent the sign, whereas B2, B1 and B0 represents the magnitude. So we have sign bit and magnitude bit. So here, since it is 0, I had said that in the previous slide, since it is, if it is 0, the number is positive, and if the number MSB bit is 1, then that represents negative. So we have positive numbers and negative numbers. So this, see here, 0, 0, 0 is 0, 0, 0, 0 is 0. Since the sign bit is 0, it becomes plus 0. So 0, 0, 1 means it is 1. 0, 1, 0, it's 2. 1, 1, 3. 1, 0, 0, 4. 1, 0, 1, 5. 1, 1, 0, 6. 1, 1, 1, 7. And the negative number, in the negative number only the MSB bit will vary. It becomes 1. Rest of the bits will remain as it is. If it is 0, 0, 0, minus 0. See here, there is the representation of plus 0 and minus 0. Their representations are different. In one case, the positive 0, the plus 0 means will be represented as 0, 0, 0, whereas minus 0 will be represented as 1, 0, 0, 0. Right? So the other method is the ones complement. Ones complement means, for example, if you have a number 0, 1, 0, 0, if I take the ones complement of this, I need to just complement this. 0 becomes 1, 1 becomes 0, 0 becomes 1, 0 becomes 1. This is what we call as ones complement. Ones complement is nothing but the inverse of the numbers. If it is 0, it has to be written as 1. If it is 1, then it has to be written as 0. This is what we call as ones complement. So here you can clearly identify the difference. There is nothing called plus 0 and minus 0. There is only 1 0, that is positive. 0 is positive. So the representation changes. However, the positive part remains unchanged. Only the variation will be with respect to the negative numbers. 1 0 0, where if it is complemented, for example, I'll take this number 1, I'll take this number as 1 0 0 1 0 0 0. What happens if I complement it? It becomes 0 1 1 1. What is the number? What this number is? If it is 1 1 1, then it is 7. So 7, that is minus 7. Since we have taken the ones complement, it is, since we have taken ones complement, it becomes minus 7. Similarly, I'll take a number 1011, that is minus 3 in case of sign and magnitude. In case of sign and magnitude, 1011 is minus 3. I'll represent it in the same way. Just a minute. So which number? 1011, 1011. If I complement it, it becomes 0100. So 100 is nothing but 4. 100 is 4. So it becomes, since it is a ones complement, it becomes -4. So this is the number -4, and so on with the other numbers. You need to complement the number and approximate it to the magnitude with the negative symbol. That's what the ones complement representation is. Whereas in case of two's complementation, two's complement, it is slightly different. It is slightly different. The advantage in case of two's complement is that there is no plus 0 and minus 0. There is no confusion of plus 0 and minus 0 as in case of the sign and magnitude and the ones complement, where we have a separate or a different representation for positive as well as negative zeros. Here in case of two's complement, one more advantage is that the number ranges from -2 power n minus 1 to plus 2 power n minus 1 minus 1. That means if I take 4, then it is 2 power 4 minus 1 to 2 power 4 minus 1 minus 1. That is 2 power 3 to 2 power 3 minus 1. The total range is plus 8, or the minus 8, minus minus 8 to 2 power 3, that is 8 minus 1, 7, plus 7. Using 2's complement method with 4-bit numbers, you can represent the numbers ranging from -8 to -8 to plus 7. This is the representation. Now what is this 2's complement and how to take the 2's complement of it? It is as simple as taking a 1's complement. The only difference here is you need to add 1 to the least significant bit after doing the 1's complement. For example, let me take 1010, 1010 as the number. In order to take the 2's complement, I need to first do the 1's complement, that is 0101, then add 1 to the LSB. This is the least significant bit and this is the most significant bit. Just add 1 to the LSB, it becomes 1 plus 1, 2, that is 0, 1 becomes carry, 1, 1 and 0. So what is the number we have taken? 1010 is the number. In case of sign and magnitude, it is -2. In case of 1's complement, the same representation can be represented as -5, whereas it is 6. 100 is 6, and since it is a 2's complement, it becomes -6. This is how we can represent the values of a binary numbers. Sign and magnitude system, in the negative values are represented by changing the MSB bit, that is B3 in figure, from 0 to 1 in the B vector of corresponding positive values, that is plus 5. So here in this example, 5 is always represented as 101. You know that 000 is 1010 001010110 and 111, that is 0 0 1 2 3 4 5 6 and 7. So now 101 is 5. 101 is 5. In case of the sign and magnitude system of representing binary numbers, if you add 0 in the MSB, that is B third, B0, B1, B2, B third position, B3 position, if you add 0, then it becomes plus 5, whereas if you add 1 to the MSB, then it becomes minus 5. This is the representation in case of sign and magnitude. Let us take another example. See here, how to represent 2 is using 0, 1, 0. Now, if I want to represent the same number in sign, that is negative minus 2, I just need to append 1 in front of 0, 1, 0. This becomes minus 2, where 1 represents the sign and rest of 0, 1, 0 represents the magnitude. So this is how we represent a binary number using sign and magnitude in the sign and magnitude system. The ones complement method of representation, the only difference with respect to the sign and magnitude is that in case of ones complement, the negative numbers are represented by complementing the corresponding positive numbers. For example, if we take the number 3, the plus 3 is represented as 0, 1, 1 is the plus 3 in 3-bit representation, or in the 2-bit representation it can be represented just as 1, 1. Okay, now plus 3 is represented as 0, 1, 1. Let us take a 4-bit representation for the explanation purpose. It can be written as 0, 0, 1, 1. Now if I complement this, complementing in sense, wherever there is 0 I will replace it with 1, wherever there is 1 I will replace it with 0. That is what the ones complement is. I'll write 1, 1 and 0, 0. Now this particular number is represented as minus 3 in case of ones complement representation. The advantage here in case of ones complement is that you can change or you can convert whenever required. You can convert a negative number to a corresponding positive value, or a corresponding positive value to a negative value as well. This way of converting either way is referred to as forming the ones complement of a given number. This particular process is named as forming. This method of forming the ones complement is nothing but subtracting the number from 2 power n minus 1. That is, if I have minus 3, for example, if I have minus 3, if I subtract this 3 from 2 power n minus 1, that is 15, that is 1111, you will get the corresponding positive number. This is what the forming of ones complement means. In case of 2's complement representation, forming the 2's complement of a n-bit number can be done by subtracting the number by 2 power n as compared to the 2 power n minus 1 in case of ones complement representation or forming of the ones complement. Only difference between the ones complement and 2's complement is the forming is done by subtracting by 2 power n. The 2's complement number is obtained by adding 1 to the ones complement of that particular number. And in case of ones complement as well as the sign and magnitude, we have plus 0 and minus. For plus 0 and minus 0, we have different notations or different representations, whereas in case of 2's complement we have only one representation for 0. There is no positive 0 and there is no negative 0. There is only 1 0 in case of 2's complement. For a 4-bit numbers, the value of minus 8 can be represented in 2's complement system, but not in the other system. In other systems, the range of numbers that can be represented using a 4-bit number is 2 power 4 minus 1, 2 plus 2 power 4 minus 1. That is 2 power 4 minus 1 by 2 power. That means it will be up to minus 7 to plus 7. Whereas in case of 2's complement, it can range from minus 2 power 4 minus 1 to plus 2 power 4 minus 1 minus 1. That is from minus 8 to plus 7. So here one extra number can be, that is minus 8, can be represented in the 2's complement system.